Good day, and welcome to our webcast, The Shape of What's Shaking, Identify and Visualize Natural Frequencies that Cause Resonance, brought to you by CFE Media and Technology. We're joined today by Eugene Vogel, Pump and Vibration Specialist, EASA, the Electromechanical Authority. I'm Kevin Parker, an editor with CFE Media. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. When machinery vibration becomes severe, resonance is often at work. Methods of testing machines for natural frequencies that cause resonance have been discussed in prior presentations. This presentation will first focus on identifying resonance and then move to methods that help visualize that vibratory motion, helping to identify solutions. Two methods will be discussed: traditional operating deflection shape, or ODS analysis, and video motion magnification. Learning objectives for today's session include a review of testing methods, how to visualize vibratory motion, operating deflection shape analysis, and understanding video motion magnification. This event is a live educational webcast presented on May 12, 2022. The educational category is Technical Health and Safety. Here are some tips to help you get the most from today's webcast. If you experience issues with the slides or audio, refresh your browser or click the Refresh Media button under the presenter's picture. Control the volume of this webcast by adjusting the volume on your computer or on the webcast platform. For technical problems with the audio or slides, click on the question mark at the top right corner of the screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask the speaker questions. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To take the Learning Unit exam, use the Learning Unit exam tab option at the top of the screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. I'd now like to introduce today's speaker. Eugene Vogel is a pump and vibration specialist at EASA, as I say, the Electromechanical Authority, headquartered in St. Louis, Missouri. EASA is an international trade association of nearly 1,800 firms in about 80 countries that sell and service electromechanical apparatus. Before joining EASA, Vogel operated his own business, General Maintenance Equipment Engineering Incorporated, or GME, a marketing, service, and training organization for industrial maintenance and related technologies. Among other courses, he taught a pumps and pump systems seminar for American Trainco. He also has extensive background in vibration and dynamic balancing and chaired the St. Louis chapter of the Vibration Institute from 1993 to 2000. Gene, welcome to today's webcast, and please go ahead.
Thanks, Kevin. And welcome to everyone. We're talking about operating deflection shapes today. When a machine has a particular vibration frequency that's a problem, has severe vibration, there's two general categories of possible causes. One is there's some fault with the machine that's generating a significant amount of vibratory force and causing the problem. The other possibility is that the machine is only generating a small amount of actual vibratory force, but the machine itself has a natural frequency which is excited at that frequency and amplifying the vibration. So in either one of these cases, and to try and determine which of them it is, it's often helpful to be able to actually visualize or see the mode in which the machine is vibrating. And that's the job of the operating deflection shape that we'll talk about. We'll talk about two different methods. The traditional method using vibration analysis, we refer to as an operating deflection shape analysis, and a new method that's been introduced in the last few years, video motion magnification. So we'll show you both of them. Operating deflection shape focuses on a single frequency of vibration. The analysis is done with the machine running, so it's the vibration generated by the machine itself that we're looking at. We record vibration data, both amplitude and phase. That's vector data. If you have amplitude and phase, you have an amount and a direction. You've got a vector. So record vector data. We'll take that vector data and we'll apply it to a wireframe model that's been drawn. And not in all cases, but if possible, we'll try to animate that model to actually show the motion. It's not always necessary to animate it in simple cases, and we'll show you both. It's important to recognize that what you're seeing is a dominant vibration frequency on a machine. We should probably explain what a dominant vibration frequency is. If you look at the sample on the left, you've got a very smooth single sinusoidal motion, a sine wave on the top, and on the bottom is a spectrum analysis of that shows a single vibratory peak. That is a dominant vibration frequency. There's only one frequency going on. In the one on the left, the one on the right, there's a number of different frequencies, and it's not quite so clear, but there is still, if you look at the waveform very clearly, a heavy sinusoidal motion going through there. And if you look at the spectrum, there is one peak that's up above 0.3 inch per second, which is a significant amount. The other peaks are lower. In this case, there is a dominant vibration frequency, that one low frequency peak. So operating deflection shape would still be useful. Even though there's other frequencies present, one of them is dominant. In this case, there is no dominant vibration frequency. So if you were working on a machine, you took a vibration spectrum, and it looked like this, an operating deflection shape would probably not be helpful in solving this problem. You'd go in with the typical spectrum analysis techniques and cursor and try and figure out what those frequencies are, what their fundamentals are, what their harmonics are, but not an operating deflection shape. So there we go. When there is a dominant vibration frequency, as we see in the samples there, we said one of two things is present. Either you've got a significant amount of vibratory force, imbalance, shaft that has pulley that has run out would generate a lot of vibration, a lot of force at one time's rotating speed, or the other possibility is that you have resonance. Resonance occurs when there's a natural frequency on the machine that's excited by that small vibratory force, so the amplitude becomes large. Let's take a look at what resonance is. So take a bar and a hammer like that, and I give it a whack. It's going to vibrate back and forth at some frequency, and eventually that vibration will dissipate, as symbolized or shown by the waveform. That's a natural frequency. You just strike something, it rings at its natural frequency. Natural frequencies are determined by stiffness, mass, and damping. To really appreciate operating deflection shape, it's very helpful to have a good understanding of what natural frequencies are and what resonance is. That's a topic for a different webinar, one we've already done, one that hopefully you know a little bit about. So if resonance is new to you, that's something you want to do a little bit of background on, so we won't go into too much more detail on that. But you could imagine a tuning fork. You take a tuning fork and you give it a whack, it vibrates at one particular frequency. Not a lot of difference between that and a machine. I'm showing a vertical machine. This is also true of horizontal machines. But you give it a whack with a mallet, and it's going to sit there and vibrate at its natural frequency. The machine's not running. We just hit it with a hammer, and it rings at its natural frequency. Okay, that's a simple bump test that is done on machines to identify what the natural frequency is. All machines have natural frequencies. If you think about it, all machines have stiffness and mass and a certain amount of damping. So natural frequency is inherent to them. That natural frequency only becomes a problem when the frequency is close to some exciting force. For instance, perhaps 1 times rotating speed being one of the most common ones. It's always been a problem with machines for as long as we've been doing vibration analysis. The more recent development of variable frequency drives or variable speed drives has made them more of a problem, has made natural frequencies and resonance more of a problem, because of machine speed now is pretty likely to find one of those natural frequencies as you move it back and forth. Stiffness and mass are the two characteristics that determine mostly where that vibration frequency is going to occur. Damping determines how severe the vibration might get. Damping is the ability of a structure to absorb vibratory energy. So if there's a machine that's bolted solid to a piece of concrete, which is very good at absorbing vibratory energy, the natural frequency may not develop a lot of amplitude because there's a lot of damping. So stiffness, mass, and damping. Much more to that than we have time to cover today. So a simple bump test will identify if a natural frequency is present or where natural frequencies are. You can do a bump test with a single channel vibration analyzer. It's a pretty simple test. You smack the machine with a mallet or a block of wood, usually not a hard-faced hammer that would create high frequencies. You're trying to excite the lower frequencies, so it's usually some sort of a softer material. And while you strike it, as you strike it and the machine is vibrating at its natural frequency, you capture a vibration spectrum with your vibration analyzer. So what you get is the amplitude and frequency data. The amplitude is not very useful. You have no way of calibrating for how hard you hit it. So the amplitude is what the amplitude is, but the frequency will indicate what the natural frequency of the machine or frequencies of the machine is. There's no provisions for getting phase data. So the only real data that you get from a simple bump test is the frequency. Typically, you'll do it on 2 or 3 different locations on the machine in a couple of different modes to see what's going on. It's a fairly simple test. This is the results of a bump test, a simple bump test. Someone took the machine and whacked it with a hammer, just like we illustrated. The vibratory results are shown in the time waveform on the bottom. You can see that there's a couple of excursions back and forth, and then the vibration dissipates as the damping absorbs that energy back out of the impact. If you did a spectrum of that waveform on the bottom, which is on the top, you'll see there are 2 different peaks that show up, one at 1350 cycles per minute, one at 1950 cycles per minute. So if the machine was a 4-pole machine running 1785, we're right in between the two, we may not have a problem. Put that machine on a variable speed drive and speed it up a little bit or slow it down a little bit, you're going to hit one of those 2 natural frequencies, and you're going to have high amplitude of vibration. So that's what you get with a bump test. What are the frequencies that are there, the natural frequencies that might cause resonance to occur or allow resonance to occur? Well, we want to talk about operating deflection shapes. And we've been talking about a bump test and resonance, which is an important thing to understand, because that's one of the main reasons we get the vibration that we want to do the operating deflection shape for. So let's look at the differences between them. The bump test is done with the machine not running. Use an external excitation. You whap it with a mallet, you whap it with a block of wood. And we get primarily frequency data, amplitude and frequency data, but primarily frequency data. That's what we get. On the other hand, the operating deflection shape is a different test we're going to talk about that is done with the machine running. So it's the machine's vibration that we're doing the deflection shape on. Lots of things can excite it. Their operating forces, certainly 1 times rotating speed is one of the most common ones, but there could be other frequencies that would excite a natural frequency or that might have a lot of force and generate a lot of vibration. When we do the operating deflection shape, we'll record vector data, which is both amplitude and phase. That's different than what we got with the bump test, okay? And we want to determine the mode shapes. We want to see the shape of what's shaking, the definition of what our title of our presentation. Moreover, we want to try to identify points of flexure that might indicate why we have resonance, if resonance exists, and it can be used for identifying mechanical looseness, and we'll look at some other things that it can find as well. So here's a picture. Here's a picture of an operating deflection shape. This is a result of an operating deflection shape. It's a pretty fancy one. This was done by a professional organization, and you can see the motion of the machine. The 2 dark blue lines that are moving in relationship to the rest of the drawing are actually the shaft motion. When they did this operating deflection shape, they had proximity probes that monitored shaft motion. That's a little unusual, so it's a pretty fancy one. But then you can also see the motion, the mode shape of how the machine casings are moving. To get that operating deflection shape, first they started with a wireframe model, okay? And they laid out on that wireframe model various measurement locations. Those measurement locations are done in both the horizontal, vertical, and axial directions. Now, horizontal, vertical, and axial are, relative to the machine, whether it's vertical or horizontal. So 3 orthogonal directions, call them X, Y, and Z. You'll take those measurements at various places on the machine. Certainly, you'll take them at the bearing location. So 4 bearing locations, 3 measurements at each. You've got 12 sets of data. Each set of data is an amplitude and phase vector. But we want to see how the whole machine is moving, so we would have defined, and there were defined on this, numerous other measurement locations at which each of those locations has a horizontal, vertical, and axial X, Y, and Z measurement. So there's, a couple of dozen measurement locations. You take three vectors at each, you're going to have perhaps 70, 80 different vector values that you're going to put into your model and let your software go to work on it and animate it for you. Okay, so a lot of data to be taken, a lot of vector data to be taken. Taking XYZ 3-axis data, you can use a single transducer, mount it in one direction, take the data, mount it in another direction, take the data, mount it in the third direction, take the data. Or you could use a triaxial pickup that has all 3 transducers built into one. Triaxial pickups you could mount in one place, take the data for all 3 at once. It's a little more difficult to mount a triaxial pickup because it has to be rigid in all 3 directions. But if you have the capability of mounting it, it certainly simplifies the data collection. I just want to mention this. It's not critical that you understand the 6 fundamental modes or anything, but if you wonder what's going on in the background when it takes that vector data, all motion can be described by those 6 fundamental modes. There's 3 directions, X, Y, and Z. In each of those, you have a rotational mode and a translational mode. And all motion can be described of a combination of those 6 fundamental modes. So if you're wondering how the software does it in the background, it breaks it down into those 6 fundamental modes, puts it in a matrix, does its computerized mathematical magic to it, and produces simulated motion. Here's a good example of what you would get out of an operating deflection shape. Chose a vertical machine because they're very common for having high vibration problems, often related to natural frequencies and resonance. And what we usually see on this is we see the motor because it's up on the top. And sometimes someone will say, well, the motor's vibrating too much. There's something wrong with the motor. What you may not realize is that down below is a pump that's going to town really severely, and it's the pump on the bottom that is shaking the motor up on the top. If you mount transducers on the pump and on the motor and do an operating deflection shape, you will see the relationship between the motion on the bottom and the motion on the top, which is what you'd like to understand. This is what a operating deflection shape on that machine would look like. One presentation of it. There is on the upper right-hand corner a 3D view showing a 3-dimensional image of what that motion is. In the other 3 quadrants, you have the X, Y, and Z view of it. So breaks it down pretty clearly so you can see just exactly what's going on. And clearly it's the pump shaking the motor in this case. Likely that pump has a natural frequency which has been excited, and that's likely what the problem is. We see some flexure in the pump column. They can be complicated. They don't have to be. Many of them are simple. But what we saw with that operating deflection shape we just showed you was a first bending mode, a read frequency mode. But machines can go into a second bending mode, kind of an S, if you will, as pictured on the right-hand side. And there can be various exciting forces. It might be 1 times rotating speed that excites it, or perhaps there'd be a higher force at 2 times rotating speed that might excite it. So you've got 1 times and 2 times exciting forces, first and second bending modes. And then if you look at that machine, it's got a discharge pipe. And on the motor support pedestal, there are cutouts which change the stiffness of the machine in line with the discharge, call it north-south, versus perpendicular to the discharge, call it east-west. So you might have a different natural frequency north-south than you do east-west. So combination, first and second bending mode, first or second rotating speed exciting force, north-south versus east-west. You got 8 different possible natural frequencies that machine might excite. Put it on a variable speed drive. Guarantee you it's going to find one of them. So this is a common problem with this particular type of machine, but on horizontal machines as well. Here's an animation of that second bending mode, and I'll use this to illustrate, just watching that machine doing the dance there, it's making my back hurt. Like, holy cow, that machine's going to tear itself up. Be aware that the animation has the ability to illustrate and change the amount of vibration. That could be a very slight amount of vibration, maybe not damaging the machine at all, but you just crank up the amplitude on the animation and make it very severe. That one's cranked up a little bit too far. Okay, just to show you what's going on. So an important point, when you see a machine doing a dance like that, it doesn't necessarily mean the machine is flying apart. It's just an animation. We can see a lot of different things from an operating deflection shape. In this instance, this might be a very, very simple operating deflection shape. The 4 arrow locations were only 4 points on the machine where vibration vectors were taken, and they show that the machine on the right-hand side is moving up when the machine on the left-hand side is moving down, and both machines are twisting back and forth. It's pretty easy from that visualization to see it's very likely that the problem causing that vibration is in between the 2 machines, which is the coupling. Very likely that machine has offset coupling misalignment that accounts for the mode shape that we see in the very, very simple mode shape analysis. So here there's no animation, not a whole bunch of data taken, just a few simple vectors, but we still have a mode shape, not an animation, but a picture of what the machine is doing that leads us to suspect what the problem might be that's causing it. So let's talk a little bit. If you want to do an operating deflection shape, what do I have to do? Well, you can do it with a single channel analyzer. Any analyzer that would do balancing will certainly do it. If your instrument has a balancing setup, you can use that balancing setup. When you're doing balancing, you're measuring amplitude and phase. Use the amplitude to indicate how much unbalance you have, and use the phase angle to indicate where the unbalance is. Those are the 2 things you need for your vector. So you can put in a balancing mode. You got a real-time display that shows you amplitude and phase, and you can just manually write down amplitude and phase for each measurement location that you want. You'll have a list of them when you're done. In order to do that, you likely will need a reference pulse pickup with some sort of a shaft marker, usually a piece of reflective tape and a photo tack. Just one little trick I'll tell you about here. We mentioned that sometimes the vibration of interest is not 1 times rotating speed. It might be 2 times rotating speed. How could I get amplitude and phase with my balancer? You could put 2 pieces of reflective tape on the shaft where your photo tack is shining, and it will see 2 pulses for 1 revolution, and your instrument will track to that 2 times frequency and give you the amplitude and phase. You can do that with 2 times, you can do it 3 times. Get very much up to 4 times maybe, but it gets really hard to get the 4 pieces of tape on there just right to get exactly 4 times. So 1 and 2 times works great, 3 is fine, 4 you get a little bit, you're pushing it a little bit. So higher harmonics are a little bit harder to track with a simple balancing instrument. If you have a vibration analyzer that don't have a balancing program in it, it likely has a mode called monitor peak and phase, or some title like that will let you monitor the amplitude and phase of the vibration, just as in the balancing program. And that varies between machines. So most machines have that. You need to check your machine manual to see how yours might be set up to do it. You can also use two-channel analyzers, and with a two-channel analyzer, you can get this done without a reference pulse pickup. So if you walk up to this machine, you got a severe vibration, and you want to get an operating deflection shape up, and you say, well, I need to shut it down and put a piece of reflective tape on the shaft. And the operator looks at you and says, you want to shut the machine down? If you shut that machine down, it ain't going to be back up and running again until tomorrow. It takes us that long to go through the cycle. So I think, well, is there any way I can get amplitude and phase data without a shaft reference? And the answer is yes. If you have a two-channel analyzer, you can use one of the two transducers as a reference. So it's put in a fixed location. And the second channel is your roving transducer, and you move it from point to point to point, from X to Y to Z, and take data. And it can compare that vibration signal from the second transducer to the vibration signal from the first transducer, just as a single channel instrument was comparing the vibration to the reference pulse. It simply compares it, the two-channel analyzer, to your reference vibration pickup. Okay? So it works really good. If you happen to have a four-channel analyzer, which has become fairly common on the market, a four-channel analyzer would allow you to have a reference pulse pickup. Sorry, I misspoke. Would allow you to have a reference vibration pickup that stayed in one spot, and a triaxial pickup on the other three channels that could move from location to location to location. So with a four-channel analyzer, you can use a triax and still do your cross-channel information. The setup on the individual analyzers varies a lot from multi-channel analyzers. So you would need to reference your operations manual for that instrument and see how to set up to do that. Here's an example of a really simple manual operating deflection shape. So there were readings taken at 5 different elevations up and down this vertical pump motor. It's typical to do this in displacement, as there are here. And the phase angles come out to be, you can look at the phase angles and see what they are, and you would plot each of those vectors as we've done here with the plotted vectors at 65 degrees, 64, 60 is pretty there, and then 235 is 180 degrees out, see it goes out the other side at the one on the bottom, okay? So to make it easy to graph, you can put this into an animation program, and you'd be done. Just put an animation program, it'll show you the motion, but I don't have one of those. I just want to see how it's moving. A pretty fundamental, easy way of doing it. So I'm going to adjust each of those vectors and turn them all about 60 degrees until they're pointed in the same direction that the transducer was pointed, and that's what you see on the right with the adjusted vectors. If I connect the vectors together, I get a straight line. That tells me that machine is wobbling straight back and forth. There's no point of flexure on this machine. There must be some, or likely is some other part of the machine that's flexing. I'm going to have to go look for that. So I'm going to expand my analysis a little bit, and let's go down and let's take readings on the base, okay, in the vertical mode. And when I take my readings on the base at the vertical mode, I get the deflection shape that's illustrated that shows a point of flexure. And the point of flexure means that that base plate down there is weak, okay? That's where my flexure is. That's if there's a natural frequency, that's where it's weak. So when I can see a weak part, then I can say, hey, what I need to do possibly is strengthen that part, raise the natural frequency above the operating speed or above the exciting force, and try to solve the problem. A word of caution, you don't have enough data here to go in and redesign this base and try and eliminate that. We always recommend that before you do modifications, you do a complete modal analysis, because there might be another natural frequency in a different mode just lurking a little bit above that. You stiffen it up, you could hit that next natural frequency. So a little bit more there than we can get into, but just a word of caution. Although I've shown you something and said, hey, if you strengthen that base, you likely could, eliminate the problem. I'm warning you, don't do that without doing a full analysis, because you get yourself into trouble with some other natural frequencies. Okay. It might also show something different. In this case, we have potentially mechanical looseness. If you have two parts that are right next to each other and one of them is moving and the other one isn't, there's looseness between them. So there's a step change in the amplitude right there. Okay, so that tells me that base plate is loose. Maybe the bolts are loose. Maybe it needs to be regrouted. But the operating deflection shape, the mode shape, really, really simple one, not even animating it, just drawing it out in a single plane, has led me to a potential problem. There's another possibility that could have occurred. These are exactly the same vectors, except for the one on the bottom. It didn't flip 180 degrees. If I plot those vectors out and connect them together, note now there is a point of flexure up and down the machine. So on that pedestal below the motor, there's a soft place there, a weak point in that has low dynamic stiffness and is allowing that to flex back and forth. Likely a natural frequency exists there. Okay. Here's an example, a real example. The vertical pump's just something similar to the one I had pictured, but this plate right here has a natural frequency below the pump's maximum operating speed. And if you see that magnet drive, that's a variable speed drive. So if they change the speed of this machine when they get to one particular frequency where that plate wants to vibrate, its natural frequency, all of a sudden the vibration goes way up. So this is a very real problem that's illustrated here. And you see the difference between that and looseness and base plate resonance. All would be indicated by the operating deflection shape. Okay. So I'd like to introduce, that's just real fundamentals of a standard operating deflection shape done with a vibration analyzer, transducer, amplitude, and phase vectors. A new method has been introduced, and this is new. This is only about 5 years. This technology is only about 5 years old. We'll call it, whoops, can't hit that key. Let me get back on track here. Here we go. And we call it video motion magnification. And it typically uses a high-speed camera to capture a video. And there are certain features in the, if you can see a particular point in there, it can track that particular point and actually detect relative motion down to 1/2 the frame rate and less than a pixel displacement. It can be really accurate with these cameras that they've got and the software that they use for interpreting them. And it'll actually produce a real-time image. They take the video, which just looks like, if you look at the standard video, it looks like a machine just standing still, and they'll amplify these features that they've picked out and make it appear to have motion that is a representation of the vibratory motion that actually exists. And they can do vibration spectrum from it also. So here's a machine. This is a fairly sophisticated piece of machinery. It's a compressor drivetrain. It's got two motors driving a gear case or a speed reducer, as the case may be, and then driving the compressor. And you can see that that second component from the right is doing quite a wobble there, and that was the subject of the problem, and they want to know what's going on. So that motion is shown in that operating deflection shape animation was produced with a traditional set of vibration data. If you look at the picture lower and to the right, every one of those labeled numbers is a measurement point. At every one of those measurement points, they took a horizontal, vertical, and axial, an XYZ reading. Man, there's hundreds of actual measurements done to do that. That's about a day's work. You could set up and get that done in a day if you had everything ready to go. So that's a fairly big investment in time and effort to set up and do the operating deflection shape, but it shows them exactly what they need to know, what's going on. Let me show you another example of the same thing. This is video motion magnification. Now, in the picture, it looks like that machine is really doing the jig, and if it really were moving that much, I would be headed out the building as quick as I could, okay? But what they've done is they've taken a very small amount of vibration, a few thousandths of an inch, and they've magnified it. They've magnified it, made it greater to show what that motion would look like, virtually the same as what we saw with our traditional operating deflection shape. So here's a little bit of a zoom in, okay? A little bit bigger picture of the same thing. You can see the motion. You can see there's some looseness in that base. That base is moving in relationship to the ground. And if you look carefully, you can see that the machine foot is moving in relationship to the base. And we could, with the camera, we could zoom in further and even do a better job of it. I don't have that available to me. You see the two little targets? Well, let me try. Just imagine that those two red circles are right around those little checkered flag markers, because that's what I was trying to highlight and I missed, okay? So those checkered flag markers there give it a really clean point right in the middle that they can track, and by tracking, you can pick up other features in the machine. You don't have to have those, but they put those on there to ensure they have it. Will allow you to actually do a spectrum analysis from the picture. Now, if I put it, they put vibration transducers on there and they measured the vibration. And when they did, this is the spectrum that they got. Okay, so that's a traditional vibration spectrum, shows a peak vibration. Okay, they took the video image and they did a spectrum analysis based on those two little targets, and there's what they got from that. Virtually the same amplitude at the target frequency of 60 hertz. There's some interference in there from the lights, less than a 10% variation. That's pretty significant to be able to go in and do a vibration analysis from a picture, from a video image. But that's what video motion magnification does for us. Okay. We looked at an image before that showed we had a step change on a vertical machine right there at the base that showed a loose, what we said was a loose base. Let's look at that with video motion magnification. There we go. Now, it's slow, so let your eyes adjust. It's not a very fast motion. But if you look at the picture on the left, you can see the whole tower of the pump moving back and forth as a single monolithic piece. And if you went down on the base and you looked at the base, and there's a zoom in here with the picture in the middle of the screen, you can actually see the looseness. You can see the mounting flange for that discharge elbow moving up and down in relationship to the base plate. So you've got a loose condition there that's allowing that vibration to occur. Okay. All right. So just to go back over it, we talked about natural frequencies, and all machines have natural frequencies: stiffness, mass, and damping. If that's new to you, you haven't seen it before, it'd be very good to go back and just look up, just Google natural frequencies, resonance. And when you have a natural frequency and an exciting force which occur at the same frequency, you get resonance. And it's like a mechanical amplifier that takes a little bit of force and makes something shake a lot. To identify the natural frequencies, the simplest test you can do is a bump test. You can do it with a single channel analyzer, and you'll determine what natural frequencies are there and see how that matches up with your exciting force, okay? That's a good thing. It's not the only thing that you'll find with operating deflection shape, but it's certainly one of the key ones that operating deflection shapes are excellent at identifying. The operating deflection shape itself illustrates the actual motion of the machine. It amplifies it so you can see it. And you can do that either with vibration transducers and some way of getting phase, either a reference pulse pickup, or if you have multi-channel analyzer, a reference vibration pickup, but you need both amplitude and phase. Without amplitude and phase, I could not have told the difference between, let me go back here for just a second. I could not have told the difference between this problem and that problem, because the only difference between the two is the phase angle of that bottom reading. And with the phase angle being different, the mode shape is different. Okay? All right. Well, we have some time. Let's see. Oh, yeah, I just almost forgot my last slide here. I wanted to caution you. It's when you see a picture like this, an animated picture like this, after viewing the webinar, go, oh, I know what that is. That's an operating deflection shape. Well, let me caution you. Pictures like this are produced by 3 different types of analysis. One of them is operating deflection shape. I could get that same picture by doing a modal analysis. With a modal analysis, machine's not running, and I go in and I smack it with an instrumented hammer, and I take a whole bunch of all the same data, but I do it with a hammer excitation or some external excitation instead of the machine's own vibration, and I can define all of its mode shapes in any frequency that exists. So it's a different test. It's one we haven't covered here, but if you looked at the picture, that could be the result of a modal analysis. Or I could go back to the original manufacturing drawings, the 3D drawings that had all the materials and their stiffness characteristics and their mass characteristics and damping, and taken that data and used it to predict statistically how the machine might vibrate subjected to various exciting forces. So there may not be a machine. I might just have the design and saying, I wonder how this thing would vibrate if I did this to it. Now, that's what we call a finite element analysis. And I could get that same picture from a finite element analysis, from a modal analysis, or from an operating deflection shape. So just a word of caution that when you see that picture, don't jump to a conclusion that it's one or the other. You need to look and see what it is that you're actually looking at. And now we have some time for some questions. And I'll turn it back over to Kevin at that point. Thank you, everyone, for attending. I hope it's been useful.
Well, thanks so much, Gene. I'm sure it was, and I have the proof because well more than 100 people joined this webcast, and the number attending has been growing all through the first 3 quarters of the program. And we've got some good questions from the audience, but we could use some more because we do have some time here. Let me start with the first one. It's kind of a big question. Someone is asking, would you mind explaining slide 17 again, please? Could we go back?
Not at all. Let me go back to slide 17. There we go. Okay. A bump test. We had a machine. We said, it's got high vibration. I just wonder if there's a natural frequency close to the rotating speed. So we shut the machine down. And let's, for the sake of simplicity, let's assume that's our machine, okay? So I went out and I gave it a wallop with a hammer, not a hammer, but a mallet. I got a mallet, and I go whap. And just as if you hit like the railing on a stair, and it went, okay? Well, the machine does that too. You may not notice it right away, but if you put your finger on when you hit it, whoa, I could feel a little bit of vibration there. So if you could feel a little bit of vibration on your finger, then the vibration transducer will take that vibration and it will, show you what it is. So the plot on the bottom is what we call a wave form. And if you just imagined, if I stuck a piece of a pencil, glued a pencil to the side of that machine when I whacked it. Let me go back up there. I glued a pencil to the side of that machine when I whacked it, and while I whacked it, I pulled a piece of paper down across that pencil. Just pulled a piece of paper down steady and then whacked the machine, okay? Well, that pencil would draw a line vertically, if I turn this thing up on end, that looks something like that bottom plot, okay? That's how it moved. You can see where the hammer hit it, and it went down, and then it vibrated back up, and it and then eventually the machine absorbed that vibratory energy, and it quit vibrating, okay? You can take any periodic signal This is a vibration signal, but you can take any periodic signal and run it through a statistical mathematical, a formula equation, if you will, process called a Fourier transform. And what it does is says, I can kind of see a waveform through there. Can you kind of see a particular frequency through there? How much is that at that particular frequency? Well, what if I checked at a different frequency and it looks at all the different frequencies that might be present and plots them out. And that's the plot on the top, and it's called a spectrum. Some people call it an FFT, a fast Fourier transformation. The explanation of how you get from the bottom to the top is much more than I can explain with a static picture. I mean, there's a couple of webinars involved in explaining that. But if you think of it as like a bar graph, you got a graph here of frequencies across the bottom. See, it says CPM, that's cycles per minute, 10,000, 20,000, 30,000. And on the right-hand axis up and down is inches per second, that's amplitude. So I have amplitude versus frequency. And you see the two cursors, there's 1 and 2. Let me highlight those. One of those cursors says there's vibration at 1,350 cycles per minute, and the other one says there's vibration at 1,950 cycles per minute. So that's the frequencies that were excited when I wallop that machine with a hammer. So if you're familiar with what an FFT is, I hope my explanation is, consistent with what your understanding was. If these displays are something you've never seen before, you've never seen a time waveform, you've never seen a spectrum analysis, I suspect that you're still pretty confused. And that's perfectly all right. This is not simple stuff to understand. It's not overly complex. You don't have to be an engineer to understand it, but it takes more than I can show you here on a picture to explain the transform between the two. So I hope that's addressed the issue as best I can.
Very good, Gene. Thank you. Quicker question. Is it typical to have a machine failure that prompts this analysis?
Kind of yes and no. A machine failure, if the machine is still running, okay, you could do an operating deflection shape on it. If you have severe vibration and you want to know why it's vibrating, yes, you could do the operating deflection shape, but the machine has to be running. If the machine has failed, meaning that it no longer runs, you can't do the operating deflection shape, okay? So you got to have it running. You could do a bump test on it after it stopped and see if there was natural frequencies, but if you hadn't done the analysis before it failed, you wouldn't have any vibration data to compare to it. I hope that answered your question.
Thank you. How is phase angle measured? I see how your transducer can measure displacement, but how do they measure movement in time?
Well, imagine that you have a piece of reflective tape on the shaft. And let's say our vibration is at rotating speed. The machine is out of balance, so you have one cycle of vibration for every one rotation of the shaft, okay? And I have a piece of reflective tape on the shaft, and I have a photo tack, a little laser pointer that every time that tape goes by, puts out a blip, 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 okay? So the time it takes to get from one blip to the next blip of that reference pulse pickup is one revolution. So if that time is, let's say, for simple say 10 milliseconds to make one revolution. So I see a blip, and 5 milliseconds later, I see the peak vibration. That's a phase angle of 180 degrees. But if I see the blip and 2.5 milliseconds later, I see the peak vibration, well, that's 90 degrees. And of course, any other proportion would be any other. So it's a proportion of the time between the blips and when the peak vibration occurs. Hope that explains it.
Good. Why do horizontal pumps often have concrete and springs on their bases?
Well, the object of that is isolation. The topic of isolation would make a great 2 or 3 webinars. It has a lot to do with natural frequencies. But the idea is a couple of possible ideas. One idea is that I don't want to transfer the vibration from this machine, whatever it might be, to the rest of the structure. I want to isolate the two. And the springs allow the machine's vibration to vibrate all by itself without any of that vibration going down on the other side of the springs. Okay, so isolation is one reason to keep it from transmitting that vibration from one to the other. Another reason, well, back up for a second. One place you might see that is, for instance, on a diesel generator, maybe in a hospital or an office building or something for backup power. They don't want to, diesels generate a lot of vibration. They don't want that vibration shaking their building. It makes noise and bothers people, so they would isolate that. I might also have a pump or a compressor or something where the piping got hot or cold and it expanded and actually moved the machine. What do you do when the pipe gets longer? Something's got to move. So they'll put the machine up on an isolation base that'll let it move a few thousandths in one direction or the other. If it were locked down solid and the pipe tried to expand and it was pushing, you can imagine the amount of stress that's going to make on the machine. So another reason they would isolate it would be to keep thermal expansion of pipes or attached ductwork or whatever from creating high stresses on the machine.
Good. When accelerometers are applied to a motor and pump or motor and fan, where are the best places to locate those accelerometers?
On the bearing locations, yes, on the bearings. If you've only got one transducer, one accelerometer to put on there, it would be a good idea to take a portable analyzer out there and measure the horizontal and measure the vertical and measure the axial. And you might find that the horizontal is higher than the vertical and think, okay, we'll put it in the horizontal direction. That's not a guarantee that it's always going to, be the best indicator, but it would be a good way of doing it. So you mount them on the bearings. Typically, the forces that cause a machine to vibrate are transmitted from the rotating element to the stationary element at the bearings. In addition, if it's a rolling element bearing, the bearing itself can generate vibration when it begins to fail, which can be easily picked up with the accelerometer if the accelerometer is mounted on the bearing.
Good. Well, we've been going at it pretty good here, Gene, for close to an hour. A few more questions, and then we'll let you take a break. How do electrical transits, that is power outages, affect the vibrations at the moment of power loss or the moment that power is applied?
That's one we're going to have to put off. It's a very complicated answer, and I would get one of my compadres who are electrical experts. I know I could tell you a few things, but it's not my area of expertise. I'm mechanical, and that's electrical. So I can steer you to 3 or 4 people who can go through a 6-pack of beer with you, answering that question.
Well, that's quite something, Gene. But thank you. To me, it's indicative of the fact that the analog is more complex than the digital. I don't know if that's a fair statement or not, but that's what I take away from it.
Okay.
Another question, how does the motor transfer the vibration to the pump, pedestal, or pad?
Well, if we're assuming that the motor is generating the vibration and the driven machine is responding, okay, then the vibration would be transmitted from the motor through the motor feet to the base, through the base, and into the driven machine. Now that happens. That does happen. More particularly if the driven machine has a natural frequency very close to the rotating speed. Okay, so you could have, for instance, a motor that had unbalance, and it's got a little bit of vibration, but it's not too much vibration, and it's transmitting that over into, let's say, a centrifugal fan. And the fan is vibrating a lot, okay? And you're trying to balance the fan, and you put the weight on, and it says move it, and you move it, and it says put it back, and it's not balancing it because the problem's over in the motor, okay? So that can happen. it'll be transmitted through the base and over to the other machine. I can tell you that's unusual. It's much more common for the fan to be out of balance and the motor to have a natural frequency. So the motor is shaking a lot and the fan's not shaking too much. And everybody's saying, oh, it's a bad motor. Well, it's not a bad motor. It's a bad base. And there's a natural frequency in the base that's letting it amplify the small amount of force that's coming from the fan. But it goes through the base. It goes through the base and up the other side.
Good. Let me ask you one final question, and then we'll let you go. But I want to thank you, Gene, for your expertise and for joining us. The final question is, simulation for a variable frequency drive or speed will have the same points of flexure, but the amplitude could multiply many times, making relative, I'm not sure, but it says deflection ratio is different. Is that a good analogy?
I think what you said is accurate. If you wanted to know more about that, I would explore something called Bode plots, capital B-O-D-E. A Bode plot is generated as you change the speed of the machine and you record the amplitude and phase at each different spot. So you have a graph of the amplitude and a graph of the phase as the machine speed changes. And that will show the change in dynamic response based on frequency, which is, it's an excellent way of identifying a natural frequency. The bump test is simple. The Bode plot requires quite a bit more setup, but I would say that what you said is accurate. Good.
To our audience, I just want to say thanks for the really great questions, and thanks again to Gene for sharing his time and expertise. Now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. Finally, on behalf of CFE Media and Technology, I'd like to thank you all for attending. That concludes our webcast. Thanks, and we'll see you next time.